Okay, so let us start our discussion today. We shall be talking about H1 in the external spiral galaxies. Well, we have already discussed in detail about H1 emission and absorption. So I will take on from there. I'll start by writing down the expression for the specific intensity. So this you should find from your notes on the radiative transfer of uh, radiation and radiative transfer of energy. And then when you go to the two-state systems, we talked specifically about H1 there. So this is the H1 specific intensity, which is defined at a particular direction in the sky. And here we have, by the vector theta, we mean the following. So we say that we see this part of the sky using a telescope. And this is the center of, so this I call the field of view. This is the center of the field of view. Imagine a Cartesian coordinate system here. So this direction I call theta x, this direction I call theta y, and any point in this can be written in terms of this vector theta. So that's what I mean by I theta. So this, when I say I theta, this is the specific intensity at that point in the field of view. It also depends on the frequency because it's a spectral line. And what is the specific intensity? So in the right hand side, I have 3 Planck constant, the rest frame frequency, which is 1420 megahertz, AUL, which you remember is the Einstein A coefficient by 16 pi. I have the column density at that particular direction. So this is the density integrated over the line of sight. The unit is like atoms per centimeter square. And then I have the line shape function, which may depend on the direction I'm looking at. It's also obviously depend on the frequency. Okay. Now, if I look at the line shift function, it can be written this way. This is a simple model for the line shift function. It will work for us. It's a Gaussian line shape function. If I integrate over the entire line shape function over nu, I will get just unity. This normalized so that it happens. The spectral line is picked not at nu equals to nu zero, but the peak is shifted there, and where nu zero is the again the rest frequency of the line, 1420 megahertz. And I get this factor, the VL, which is the line of sight component of the velocity of the cloud divided by the speed of light. Sigma nu is the width of the line. Well, what is VL? The line of sight component of the velocity of the H1 cloud. It has 2 components. Now the H1 cloud from which the emission is coming, of which this is the specific intensity, is a part of a galaxy. So it's a part of a galactic disk, which I have drawn with this cartoon. And this galactic disk, all the galactic disks can have a certain velocity with respect to us. So the galaxy itself may be moving away or coming towards us. And that you can imagine as the velocity of the center of the galaxy if you wish. And that I have written as in terms of Vg. So this is the line of sight component of the galactic receding velocity. On top of that,
I didn't get that.
On top of that, sorry for that interruption. On top of that, I also have this disk being rotated. And because this disk is rotated, again, from the rotation, I will get a line of sight component of the rotational velocity. And now that will be different at different position of the disk, because if you imagine this is being rotated, this part is going away, so it will have a certain velocity of going away, but this part will be coming towards you. So it will have a certain velocity of which is towards you. This is the velocity which is going away. So the line of sight velocity is clearly different at different parts of the disk. On top of that, the disk not need to be in a face-on orientation, and by this time you know what is face-on, where you can see the entire disk of the galaxy like this. It can have any orientation, and the orientation it has with respect to face-on, we call it inclination angle. So if it has a certain inclination angle, then this line of sight component of the rotational velocity will be related to the tangential rotational velocity, which is the velocity that is being shown here essentially. What is the, if I draw, if there is a cloud here and it's going this way, at this particular point, it has a velocity pointing this direction. So that's the tangential rotational velocity. And if I take the modulus of that, then the line of sight component of the tangential rotation velocity is related to that, the line of sight component of the rotation velocity is related to the tangential rotation velocity this way. This you can figure out just doing a coordinate transformation. And the inclination angle appears here. For a typical galaxy, the inclination angle itself can be different at different radius. It is not necessary that at all the radius the disk has the same inclination, but for the time being we are assuming it has the same inclination. Also, the disk orientation I have shown that the inclination is keeping this axis constant, but this axis can be anywhere. So this ellipse now can be rotated like that or anything that you may like. So all these are possible. So these are uh, the components of the specific intensity that we have talked about. So till now we have discussed what is the specific intensity, what are their different components, column density, then the line shape function. The line shape function has this VL, which is the line of sight component of the velocity, which has the galactic velocity plus the rotational velocity. Now, what are the observables? One of the observable is the specific intensity itself. So it will be a function of 2 theta and 1 frequency. So this will be given as a function of 3 variables, which means I can think of a cube in which this function is given. Cube means cube has 3 axes, and along these 3 different axes, I can have theta x, theta y, and nu. Or what you can do is you can think of different parts of the cube. Like for example, if I have a cube, I have this different, just a second. So let me draw for you what I mean. So I have this one square in the cube, and then I have another square, then I have another square. So let me give these a different color so that it is easier for you to understand. I have another square, and then if I choose a different color, I have another square, like that. So the cube now I have broken up into different squares, and for different squares you may think that the frequency is different, and these are like the x and y axis that I was talking about. So this is one way of looking at the data. The other way of looking at the data is integrating this over different things. So let us look at those observables. So here I point out those observables. So I take this and I integrate over all frequencies. So what is that you are expected to get? Well, the frequency dependence in this only comes in the line shape function. As I have said, it is defined so that if I integrate it over all frequencies, you just get 1. So then what I will be left with is the column density multiplied by this number. So this is a number which you can calculate given that you know H, nu naught, and AUL, and that those things are quite well known. So you can calculate these numbers, which means that if I integrate this over the frequencies, what I get essentially is column density scaled by a known number. So I can get the column density out of it. So this is called the moment zero map of the galaxy. And we'll look at the moment zero map one of the galaxy, real galaxy today. So this gives you the column density. Then what I can do is I can multiply it by nu and then integrate over all nu, sorry. So I can multiply the specific intensity by nu, the frequency at that particular that nu, and then I integrate over all nu. So what will happen then? Well, if you look at again, the nu dependence comes from here. So this is a Gaussian. If I integrate a Gaussian, multiply it by nu, what I am supposed to get back is this, which has the information about the line of sight velocity. It will be scaled by the moment zero map. So usually when you define this as the moment one map, you divide or scale it by the moment zero map or normalize it by the moment zero map. So this now has the information about the line of sight velocity. So you see the physical parameters of the galaxy, the column density, which is related to the density of H1, the velocity, which is related to the dynamics of the H1, these you can get from the moment zero and the moment one map. But remember that these are function of theta, which means you have to have a telescope which is good enough such that you can resolve the galaxy. You can look at different parts of the galaxy separately. If you don't have such a telescope, which is the case of the single dish observations in radio astronomy, then obviously you cannot integrate, you cannot look at different theta separately. You essentially see an integrated effect. So that's what a single dish telescope will see, where you will essentially integrate the specific intensity over all theta directions. And if you do that, what will you get again? If you do that, I have now integrated over this. So what I will be left with is the line shape function. But you remember that the line shape function is also a function of theta. So I will get not a Gaussian, but a more complicated line shape function, which will tell us more about the galaxy. Even interestingly, it tells us about something about the rotational velocity. Okay, so this is what I wanted to tell you about the theory part of it. And now what we will do is we'll look at some real data, and we'll use a software to do that. So let me first introduce to you two URLs, universal resource locators, from which you will get the data, which is this, and the software which we'll use called Ds9, which is this URL. So what are these supposed to do? Well, this data has this has the H1 data cube, which is essentially what I was talking about when I said that specific intensity is itself a, a, a data product. So it's a function of three coordinates, theta x, theta y, and nu. It also gives you the moment zero and the moment one maps of many spiral galaxies and other types of galaxies called dwarf galaxies also. And this is a software which is for data visualizations and some very basic analysis works. So we'll see how do we get some of these quantities that we talked about here. So this quantity, these quantity, and how do you get an idea about the tangential rotation velocity as well as the galactic velocity from these data cubes. Okay, so let me show you a nice picture of the thing survey. So it's a survey of, it's called H1 nearby galaxy survey. So many nearby H1 galaxies have been observed with this. And these are the moment zero maps of these galaxies. And the particular galaxy we're looking at today is NGC 2403, which is here. And once you go to this, that URL that I have given you, you see a download chart like this, where this column gives you moment zero, this column gives you moment one, and this gives you the cube that I have talked about. So for example, if I put the cursors so here and right click and say download, it will download a map of 2403, moment zero map or moment zero image of 2403. So this is the data. This is the name of the data essentially. There are two types of maps here. Let's not bother about it. We will use only one type. Okay. So what I will request you to do after I do this exercise today is take your breath so the next week I will not upload a lecture for the first day. So this is the last lecture on the Galaxy series. We will start Cosmology series afterwards. So in the Galaxy series, I will not upload another lecture in the next Monday, which is when it is supposed to come. I'll start Cosmology from Wednesday. But what you are supposed to do by Monday is each one of you should download one galaxy. It doesn't matter if somebody else has already downloaded it, the data of it, and play with the data as I show you today. and produce some results. And I will tell you what to do. Okay. So as you may already imagine that I have already installed the DS9 software, and the DS9 software interface looks like this. Here I have this button called file, which if I click, I can actually for some reason it's not working. It seems. Let me just check. So if I click on the file, then it is supposed to give me a way of importing that file. So okay. So if you click on file, so it's outside, the window is opening outside your field of view in this. So what it will give you is it will give you a browser window from which you can download the file. So let me try to see if I can do it here. For some reason, it's not working very well with the Zoom. So what I will do is I'll just come out of Zoom. It's very trivial to open a file. I think that all of you have done it many times. I'll come out of Zoom and first I will download a file. I have downloaded the file. I will open it in the DS9. Okay, so I have opened the file here. It looks completely noisy, and you'll see why it is so shortly. So let me show you that how I can see. So this is only showing a part of the galaxy. So if I click on zoom and then say zoom fit, so which is here, then it shows the entire image. Okay, and with the image, I also get this slider because the file that I have opened is the data cube, which means I am seeing only one of those squares, and once I can go to different squares, I will see different frequencies. And I can change the frequencies here. And as you will see, so when I come to this frequency, there's some emission start to appear here. And as I move across the frequency, you see that the position from where the emission is coming is changing. This is just because at this frequency, the galactic emission comes from this region just because of the galactic rotation. So this you can see that now it is going around the entire galaxy. Okay, so this is the first thing that I wanted to show you. You can open the cubes. The cubes are a little bigger file, but anyway, you can open the cubes and see how the emission is coming from the different parts of the galaxy. The center of the galaxy seem to have no emission, no shift. So that's the center of the galaxy. So it's being, the emission is there, little bit emission is there in almost all the frequencies. Okay. So because this is open, so let me show you something that we can do with this data. So first what I do is I go to edit and select region, which let me choose different regions on top of this. And as you can see, when the galaxy moves, it kind of traces an ellipse over here. So I will choose an elliptical region. So I go to region, and here again outside your field of view, I can choose different regions, and I go to shape and I choose ellipse. Okay, so once I choose the ellipse, now I can draw an ellipse on top of my screen. Okay, I can double click on the ellipse, and that gives me this window where I can put the different parameters of the ellipse. Now the angle in which this ellipse is oriented comes out to be 34 degree. I will tell you how do I get that angle. And then the center of the galaxy I can choose. So here, when it has written the center of the galaxy, it has written in array and right ascension and declination coordinate. That's a kind of little inconvenient for us, but we can choose the image pixel coordinates. The image is an image which is 2048 pixels by 2048 pixels. So 2048 this way and 2048 this way, which means the center will be at around 1024. So I just choose 1024 here. And so I say apply. So what it does is it makes an ellipse as I would have required. So it essentially incorporates the entire galaxy inside the ellipse approximately. Once I have done that, I can now integrate over the entire region in this ellipse and plot that as a function of the frequency. So, sorry, I double click on that ellipse and I make sure that it is 1024 by 1024 at the center because I accidentally shifted it. Okay, so once I double click on this ellipse, again outside your field of view, so let me increase the field of view a little bit, sorry, it will, unfortunately the uh, Zoom will not allow me to show us that part of the screen, but you will see there is an analysis bar that appears, and that in that analysis bar, there is an option for plot 3D. And once you click that, it will take some time because it is doing the integration, and then this comes. So what do you see here? First of all, so x-axis is the velocities compared to the center of the sun. So if you are sitting on the sun, what will be the velocity of different part, or the velocity corresponding to different frequencies. So it is converted to velocity already. Y-axis is the total intensity. So this is the last S as a function of nu that I was talking about, that is being shown here. So as you see that this has what is known as a double hump structure or double horn structure. So this is one horn, this is other horn. This is approximately the center of the frequency channels. Now it turns out the distance between these two horns are given by this formula. The distance between these two horns are essentially 2v0 sine I. So what is v0? So v0 is the, when you learned about, so the distance, sorry again, how do I go there? Okay, no. So always tries to move the screen only. Is all right. So I come back here. The distance between the two arms is given by 2v0 sine of the inclination angle. The inclination angle we have already talked about. V0 is the velocity far from the center of the galactic disk. Okay, so this is the distance between these two horns. So if I have gotten this picture, so then I will get the value of V0 sine I. On the other hand, if somebody have told me that the galaxy stays within that ellipse, then I can say that this is a projection. So I know that the semi-major axis and the semi-minor axis will essentially give me what is the inclination angle. So from that and to V0 sine I, I can figure out what is V0. Okay. So this is the data cube. Now let us move on and let us look at the moment zero map of the galaxy. What is the moment zero map supposed to give us? Remember that the moment zero map is supposed to give us the column density of the galaxy. Okay. So let me again go off the screen and load the moment zero map here. So moment zero map is supposed to give us the column density of the galaxy. It's the integration over frequency of all the other all the channels that we are seeing there. So this is the moment zero map. Now in DS9 you can see it in many different ways. So let me just show you once. that you can choose different types of colors. So for example, I can choose it this way or that way, or this way, and I can change the color map of the galaxy. But that's not what we are interested today. So let me just keep it for you as the uh, as the just grayscale map. What we want to do here now from this, what is that we can figure out? So this is a representation of the column density of the galaxy. First thing that I request you is to look at the data and try to figure out how to know the column density of each of these pixels. It may not be easy for you, but give it a go. Try to figure out the column density of each of these pixels. Tell me the number what you get. So I will put an exercise. So tell me the number you get and the class note comments of this particular video. Okay. The other thing that I can do is I can figure out what is the radial profile of the H1. And how do I do that? If it would have been a circle, I could have put just annulus regions, annular circular regions, but it is not a circle, it's kind of ellipse. So I have to put annular elliptical regions. And the region again offers me option for that. So I can go to region shape and then elliptical annulus, and I can just initially draw something on here. Again, if I double click on it, it opens a window which lets me draw elliptical annulus. So let us see that what it will do. So again, for angle, I put 34 degrees. And if I say generate and apply, you see that the annulus has rotated. So there is only one annulus here because the number of annuli is one here. So I need at least 32 of them. The lowest, the innermost and the outermost circles you can choose. So I can choose them in image, which will let me choose in pixel. So let us start the annulus at 10 pixel and go up to say 800 pixels. I'm sorry. So the inner is here. So I choose 10 pixel and outer I go up to say 800 pixel. And this has an inclination angle. So this will be more like 700 by 800 will give me the proper ellipse. So I will tell you how to get these numbers. I go to image here again and I choose a center 1024 by 1024 and 32 annuli. I say generate, so it generates the boundary of the annulus, and once I apply, it shows me the this. As you can see, I should use larger number here. So let's put 900 here. Say generate again and say apply. And that still doesn't do justice to the inclination angle. So I put 600 here and say generate and apply. And that gives me fairly good coverage of and ellipticity for this particular galaxy. Okay. So once I do this, so it has now created these annuli. And for each annuli, it can calculate now what is the total emission in each annuli. So if I double click on that, again outside your screen, it opens an analysis tab. And in that analysis tab, I have the option to see the radial profile. So once you click on it, it will take some time to calculate the radial profile. Radial profile is what you wanted to get from here. And let's wait. And let me show you the radial profile has come along. So this is the radial profile. So you see what's happening here is x-axis is in arcsecond, the y-axis is surface brightness. At the center of the galaxy, it is low, and then it goes high, and then it keeps on decreasing. This is quite the case for all the spiral galaxies. At the center, it is low because remember, at the center, you have that bulge region where there is a lot of star formation, and that depletes the H1 content in the center of the galaxy. So you should look at the other galaxies for which you get the data. but that this actually is the case for this galaxy. Okay, this is the exercise that you can do with the moment zero map. Two exercises. One is to figure out the column density. The other is to figure out the radial profile. Okay, so I'll pause here again and load the moment one map and then come back again. So what is the moment one map supposed to give you? Remember, the moment one map supposed to give you the line of sight velocity. It means that if I look at the moment one map, which we are looking at right now, it is supposed to have some velocities in some place and some other velocities in some other place. So if I move my cursor here, you see the value at the point of this cursor is given here in this command, in this box, which is the velocity in meter per second. So value here is, if you look at the box there, 246 meter per second. If I go there, it becomes 250 meter per second. If I go at the center of the galaxy, remember the center of the galaxy has no rotation, so this is supposed to give me the velocity, receding velocity of the galaxy, the line of sight component of the velocity of the galaxy itself, which is 116 kilometer per second. A little better way of getting that is to select a region here and calculate the average velocity in that region. And to do that, again, I can go to the analysis tab and now select a region. I go to the region tab and select a region which is a circular region and put a small, very small circle there. Double click on that. So any region I can double click and change the parameters. And I make sure by choosing image here and 1024, 1024 that I am looking at the center of the galaxy. As long as the circle is small, it doesn't matter how big the circle that we want to choose. Okay. So again, once I double click on this, there is an analysis tab that comes in, and it can show me now the histogram of the pixel values, so histogram of the velocities. So there are different values at different velocities. We want to ask that what is the mean of this, which will be approximately the center of the histogram. So here, the center of the histogram, you can see this is approximately the center of the histogram. And this is 100, this is 150, which means this is 125. So this is approximately at 112 kilometer per second. Okay, so 112 kilometer per second is the galactic velocity. So you have to subtract that 112 kilometer per second from all the velocities that we get. So you have to remember that. So from each point in this map where the velocity, galactic velocity is calculated, the galactic velocity, line of sight velocity has two components, if you remember. One is the receding velocity of the galaxy itself, which we have just calculated 112 kilometer per second. Another is the rotation velocity. And now let us look at the rotation velocity. So if you want to calculate the rotation velocity, first you have to subtract 112 kilometer per second from all the points here. So just keep that in mind. So I can remove this particular region, which is a circular region, just pressing the delete button with my keyboard, which I have just done. Now what do I do is, I choose, see, it is clear that the maximum of the velocities are along this line and the minimum of the velocities are along this line. So what is plotted here is the velocity, which is the velocity of going away from us, which means that this part is coming towards us, this part is going away from us. Here along this line and along this line, the velocity is not supposed to change much. The way you can check it is we can choose a line now and ask for the statistics along the line. So what it will do is it calculate how the velocity changes along that line. So to do that, We go to region again and choose a shape which is a line and draw a line. So let us first draw a line like this, which is in a direction where supposed to be there is no change. And I can choose, I'm sorry, I can choose the center of the line to be again 1024, 1024. It don't matter much how much it is rotated here. We're just looking at it. So if I double click on this, again an analysis step comes and I can say plot 2D, where it is supposed to plot the variation of the velocity along that line. And if you look at the variation of the velocity, there is not much variation of the velocity along this line. It's almost constant, right? Okay, so it's true that there is a little bit less here, but if you look at the axis levels, it goes from some 115 here to 140, so it's still not much variation. Okay, what happens if I move the line this way? This is the direction in which you are supposed to see the maximum variation. And you see that, and you see clearly there is, so it starts from, see this is 150, so which means it is 175, 125. It starts from 112, which is the center part of the galaxy. It rises and eventually it becomes constant here. So when it becomes constant, it is 250 kilometer. And that is the value of the V0 that we were talking about earlier. So this, what you are looking at, is the rotation curve of the galaxy, which Vidya has talked to you about, and which is the rotation curve which was used to figure out that we have dark matter as a component of the galaxy. Okay, so that is what I wanted to show you today using this software. So what I request you to do is to post your plots of rotation velocity, the total spectra S which we got from the data cube, and the radial variation of the column density which we got from moment zero map. So moment zero map, radial variation of the column density, moment one map, the rotation curve, and the data cube, the total spectra. These three things you do from randomly different galaxies in that database. So this is your exercise, and I request you to finish this exercise and post your plots as comments in the, I will put an assignment link for this. You may submit the assignments in that link. Okay, so that's it for today, and that's all from the galaxy part of this course. So we also have covered the interstellar medium in the last 3 lectures in the same course. The next lecture will be on Wednesday, where we'll start talking about cosmology, which is studying the universe as a whole. Thank you. Goodbye till then.